Now let's look at example 7.4.2. For a class project, a political science student at a large university wants to estimate the percent of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Compute a 90% confidence interval for the true percent of students who are registered voters and interpret the confidence interval. So let's start out. We notice we're being asked for a true percent of students. This is just a fancy way to say proportion. So we're doing another proportion confidence interval. Some more information that's important. He surveys 500 students, finds that 300 are registered voters, and also we have a 90% confidence interval. Let's write this information down. The survey, N is 500, X is 300. Put these together to get our sample proportion. 300 divided by 500 would give us 0.6. We can then find Q prime as 1 minus P prime. So Q prime is 0.4. Since our confidence level is 90% or 0.90, alpha is 1 minus our confidence level. So alpha is 0.1. Alpha over 2 would be 0.1 divided by 2, which is 0.05. Since alpha is 0.05, I can look up what z alpha over 2 should be. Norm.s.inv, alpha is a probability, so I'm going to put in 0.05 to the inverse function. And I get 1.6448, 1.645, or 1.65. We usually use 1.645 because it comes so close in the middle. And if we round too much, we can get off on our answers. So 1.645, this value is returning negative because I used 0.05 to the left. So I'm getting the negative z value. But remember that the standard normal is completely symmetric, so if I'm looking for 0.05 to the right, I just change the sign for that standard normal to a positive 1.645. So the z alpha over 2 that I need, we just want the positive one, 1.645. Now, given all that information, we can calculate our error bound for the proportion. Z alpha over 2 times the square root, P prime, Q prime, over n, plugging in the numbers that we have, 1.645 times the square root, 0.6 times 0.4 divided by 500. We can pull up our calculator to do this. And looking up top, I see I have 1.645 times the square root, 0.6 times 0.4 divided by 500. And if I hit enter, I get 0.036 for my error bound for the proportion. I take that error bound and I take my p hat, and to set up the confidence interval, my population proportion, p is in the middle. P prime plus 0.036 for the error bound, P prime minus 0.036 for the error bound, and I know that P prime is 0.6, so I need to do a quick calculation here, 0.6 minus 0.036, and we get 0.564. So P, the proportion, needs to be between 0.564 and 0.636. Or, if we talk about interpreting that, we estimate with 90% confidence the true percent of students who are registered voters is between 56.4% and 63.6%. We could do this exact same problem using the template. So here I have the template. Notice at the top it does say confidence interval for the population proportion. We will have different templates to do the other ones, the other confidence intervals, if if we're not doing them by hand. We generally don't know the size of the population, so capital N is usually left off. Sample proportion, we calculated it above, but we're going to pretend that we didn't do all of that work that we already did. So we're just going to put in what's given to us in the problem. We do have the number of successes. 300 students were registered voters. Our sample size, we polled 500 students. And for our confidence level, we had 90% or 0.90. Once we do that, notice that all of the other cells have numbers in them, calculations. And specifically, we were looking at these last two boxes. The lower confidence limit, 0.5639, that would round to 0.564. And then our upper confidence limit, 0.6360, that's our upper confidence limit. It's exactly the same that we got when we did it by hand. And we would have the same interpretation.